Okay, and now we can move on to the same thing, proving the same statement. Let me copy this down here just so we can have it as a reference. We're going to prove the same thing using a truth table instead of doing it algebraically. And this is going back to what we were doing in that first chapter using truth tables. And the stuff that we're actually doing in this section or in this chapter is very much the same as the stuff we were doing in that first chapter. We're just approaching it in a different way, in a way that is more convenient for certain things, doing things in terms of variables and with these operations and treating it like algebra is really useful for certain things. We'll get more into that in the next section. For this section, though, we're not going to think too much about sort of what these operations. This is something I want to note. These plus and times and this complement operation, these have certain meanings that we can translate back into what we were talking about in the first chapter, talking about logic and truth tables. But that's going to be more something we'll look at in the next section, what the interpretation of these different things will be. But for right now, all we need to do is fill this out like a truth table. We can put trues and falses in here, but to stick with the algebra, with the notation we're using here, we'll use zeros and ones. So let's say we have false, false, and then true, true, and then false, true, or just zeros and ones representing those two states. And then again, we could think about sort of what operation is, if this is an and or an or, and how those would, how these two values would combine together using that operation. But we're just going to think of this like plus and use those same properties to work these out. So for instance, if we look at the addition properties, we can see things like x plus 0 is x. So anything plus 0 stays the same, which is what we'd expect from regular algebra. And then anything plus 1 is 1, which is not what we'd expect from regular algebra, but this is a property of Boolean algebra. So we can start here. We can say if we're adding 1 to anything, it's always going to be 1. It always gets stuck at 1. So 0 plus 1 has to be 1, 1 plus 0, and then 1 plus 1, those would all have to be 1. And then 0 plus 0, again going back, anything plus 0 is itself. So if we take 0 plus 0, then if you say you're adding this to 0, then this is going to be the answer, and the answer is 0. And just based on this truth table that we just made, you might be able to predict what this operation represents. We can compare it back to those truth tables we've seen before, but we'll just keep going here. So next we need to fill out the complement operation, so x complement, and that should be easy. That's just the opposite of each of those. Anywhere we have a 0, we put a 1, and vice versa. And then we want to multiply together x complement and y. So now we're looking at these two columns, and we want to multiply those together. So now we'll look at the multiplication properties here. So we have similar things here. We have anything times 1 is itself, and then anything times 0 is 0. And this is actually something we know from regular algebra. This is true with regular numbers as well. So anything times 0 is 0. So that means if it has a 0 in it, it must be 0. So all three of those would be 0. Is that right? And then this, oh, sorry, no, I'm looking at the wrong two columns. We have these two columns. Okay, so this has a 0 in it, and these two. These all have zeros. This is 1 times 1, which, just to double check here, anything times 1 is itself, so 1 times 1 would have to be 1. So that would be the column for x complement times y. And then finally on the side here we have x plus x complement times y. So now this is adding together these two columns. Adding together those columns. And remember, if we're adding 0, let me just double check, make sure I get this right. If we're adding 0, it stays the same. If we're adding 1, it becomes 1. So if we have any 1s in here, 1 plus 0, that's got to be 1. 1 plus 0, that's got to be 1. So those are 1s. And then here, 0 plus 1 has to be 1. 0 plus 0 would have to be 0. again, using all that same addition logic. So then finally, here's our full truth table. And it was laid out for us what we're actually finding here. But again, the reason we're doing all of this is we want x plus y and we want x plus x complement times y, because those are the two sides of our equation that we're trying to verify. And so in order to verify that equation, we're basically trying to check if these two columns are equal, and they are. In the truth table, they have the same values, so those must be equivalent statements. And the only reason this whole thing works is there are only two possible values for these variables to take, true or false, or 0 or 1. If these could be other numbers like 1, 2, 3, 4, 5, 6, we wouldn't, well, the more numbers we have, the bigger this table needs to be to think about all the possibilities of adding or multiplying those numbers together. And if we're actually talking about any numbers, if these are integers, then this table would be infinitely large. But the fact that a Boolean algebra is only allowed to have these two values in it means that we can actually go through all of the possible combinations, or we can perform that operation in all possible cases and then see exactly what the outcomes will be. And if they're all the same, then by definition those have to be equivalent statements. We could add on one other, if you want to kind of relate this back even further to what we talked about in the first chapter, we could add a column here that set these equivalent to each other. Make sure I find the right arrow. Oops. Something like this. So this is a column that's checking if this x plus y is equivalent to this other thing. And the way we check this is we look at these two columns, and anywhere where their value is the same, we get a 1 or true. And anywhere where their values are different, we'd get false, but they're all the same, so we get all true. And because this is all true, we would say this is a tautology. And a tautology statement means that this statement that we've had up here is true. It's a verified formula or equivalence or whatever. So this is confirmed. We don't have to go this far to do this extra column, but just by showing these are the same, we've verified that equation.